Hello everyone, I'm Zhao, a principal scientist in customer trust and partner support at Amazon. In this talk, I'm going to introduce a new active learning method to reduce the labeling cost. During the talk, I will describe the problem, the drawbacks of existing active learning methods, our proposed approach, and the results. Let's start with the problem. Supervised learning has been widely used in various areas in Amazon to improve the efficiency of our machine learning models. In our org, we rely on these models to estimate the risk of different events. However, to train our models, we require high-quality labels. These labels are expensive. As our business grows, our reliance on reliable labels is also growing, and we estimate that to represent a growth of 30% year-over-year for the past few years. In order to improve the efficiency to scale our business, we are looking into active learning to build our machine learning models with fewer labels while maintaining the same performance. Active learning is an approach to select unlabeled data for labeling by an oracle, and then use those labeled data to train a classifier. This happens sequentially until we get to a good performance. At each step, the active learning agent selects the most informative data samples for labeling, which improves the classifier's performance the most. So, with an efficient selection approach, we only need a small amount of labeled data to train the classifier. The agent itself can be composed of rules or algorithms. However, existing active learning methods don't meet our needs. For example, in the traditional active learning framework, we select one sample at a time, and then retrain the classifier with the newly added labeled data. This is quite slow, since we would need to retrain the model thousands or millions of times. This makes the traditional active learning approach prohibitive for our use case. Therefore, we need to use batch mode active learning, which can dramatically reduce the training time as it selects a group of samples at a time. However, selecting a group of samples to improve the classifier's performance the most is a challenging problem, since there are many combinations. For that, the existing batch mode active learning techniques use either heuristic criteria or the full optimization method. The heuristic criteria, such as uncertainty scores or diversity scores, are relatively slow and provide low performance for imbalanced datasets, which is our use case. The full optimization method is suitable for small-size datasets and is hard to scale to our use case, which contains millions of data samples. So we propose a new batch mode active learning method. In our method, the core idea is to train an agent to output one ideal sample at a time, and then repeat this multiple times to generate a group of samples for each batch. In our implementation, the agent, or as we call it, a policy network, is in fact a deep neural network. The input of this policy network includes the current available information, such as the summary of the selected samples, the summary of the already labeled samples, the summary of the unlabeled data pool, and the classifier performance. There are different ways to implement a data summary. In our method, we use the percentiles of features as the summary for the whole dataset. Each time, we run the policy network to output one ideal sample, and we select its closest data sample in the unlabeled data pool. The selected sample will be removed from the unlabeled data pool and added into the selected dataset. So, when we run the policy network next time, the output will be different. In each batch, we repeat this multiple times to generate a batch of data samples for labeling, and then train the classifier. We repeat this for many batches until we get a good performance. Our method can scale to large-size datasets, since the size of the policy network stays the same when the size of the dataset increases. This is the goal we had in mind when we designed our method from the beginning. We use imitation learning to train the agent or the policy network. For the imitation learning part of our method, we need an expert to generate a perfect policy, and then let the policy network learn it. After that, we can apply the trained policy network to our use case, as we explained before. To generate a perfect policy, we need a fully labeled dataset. Here we called it the source dataset. As the separation of the source dataset, we will call the dataset we're going to label the target dataset. On the source dataset, we simulate how an expert selects the most informative data samples for labeling and train a classifier sequentially. We can easily do this simulation because we know all the labels in this dataset. At each simulation step, we generate data pairs, which include the current best sample for labeling, given the already selected samples, the already labeled samples, and other status information. These data pairs represent the perfect policy. Then we use these data pairs to train the policy network. Once it learns the perfect policy, we can apply it to our target dataset to select samples for labeling. This is basically transfer learning, since we transfer the policy learned from a source dataset to a target dataset. Where can we get the fully labeled source dataset? In our case, we can use historical labeled data. We also tested our approach in some public datasets. Here we show the results when we applied our method to one public dataset. It is called Stormfront dataset, which includes hate speech posts. This is our target dataset. The source dataset we use to simulate the best policy is another public dataset called English Hate Eval dataset, which was collected from Twitter. After we trained the policy network, we applied it to the Stormfront dataset to select the best samples for labeling. This is a highly imbalanced dataset, which means one class has many more samples than the other class. It shows that our method only requires 200 carefully selected samples to reach the best performance, something existing method cannot achieve. Our risk evaluation use case is also composed of an imbalanced dataset. We trained the policy network, used an old dataset, and applied it to the most recent dataset. It showed that we can reduce the number of labels to 3% while maintaining the same performance. If you would like to learn more details, you can read the paper we published in IEEE International Conference of Data Mining 2021. This is one of our interesting examples of applying machine learning techniques to address our business challenge. If you are interested in joining our team, please check our career page. Thanks for watching.